Rachel Micander, and I'm a geologist with the Nevada Bureau of Mines and Geology. And today I'm going to talk to you a little bit about rocks and minerals and where they come from. So for us to first start talking about rocks, we need to first talk about minerals. So what is a mineral? A mineral is a naturally occurring inorganic substance with a definite chemical composition and crystalline structure. I have a couple samples of Galena right here, the mineral for which this park is named for. So certain things can be minerals, and some things that are commonly thought to be minerals are not actually minerals. A couple examples of those would be materials such as coal and amber. The reasons that these two are not considered minerals is because we have to take a look at our definition of a mineral. It has to be naturally occurring, inorganic, which means it can't come from something that was once living. So let's talk about coal and amber. Coal and amber both came from something that was once living. Coal comes from a decomposing organic material that over time turns into coal, whereas amber is simply petrified tree sap. So now that we have a basic history or basic background of our minerals, let's talk about rocks. So rocks are naturally occurring solids that are composed of one or more minerals. There are three main rock types, and those are igneous, sedimentary, and metamorphic. So let's talk about igneous rocks first. Igneous rocks are rocks that come from fire. We have two main types of igneous rocks: extrusive igneous rocks, or volcanic, and intrusive igneous rocks, or plutonic. Our extrusive igneous rocks, as you would guess by the volcanic name, come from volcanoes. These originally come from lava. And so to talk about igneous rocks, let's backtrack a little bit and talk about both lava and magma. This is molten rock. Magma is the term geologists use for molten rock when it is underneath the Earth's surface. When that magma is erupted out onto the surface through a volcano, the term used is lava. So our volcanic rocks, which I have a lot of volcanic rocks here because honestly they're my favorite. Our volcanic rocks are rocks that come from lava. We have a few different examples here. We have a nice piece of pumicey vesicular basalt type rock right here, and you can actually see the surface we call flow banding. What happened here is that we can see the remnants of the direction of the flow when this rock flowed from the volcano. We have pumice, which is really light and airy. It's full of bubbles. Another word for it is vesicles. And then we also have obsidian, or volcanic glass. Here's some basalt. This came from the Columbia River Plateau. These were called flood basalts. They were massive massive lava flows that flowed out over hundreds of miles and spread these layers of volcanic rocks. And you find these up there, and that's what we call basalt. And then right here we have a rock called Nevada Wonderstone, and this is actually a rhyolitic rock, so a volcanic rock that has been altered by water. This is why we see these nice little bands. So talking a little bit more about our igneous rocks, our volcanic rocks cool really, really fast. So when they're erupted from the volcano, they have very little time to cool, and depending on their composition, they will, if the lava they came from was very viscous and bubbly and frothy and had a lot of dissolved gases, those gas bubbles will be solidified in the rock, just like this pumice is. Other rocks are more smooth, like the basalt we talked about earlier, and even smoother is our volcanic glass or obsidian. So these guys in particular cooled very, very, very slowly. Basically cooled so slow there was no time for crystals to grow. Now let's contrast that with our intrusive igneous rocks. So another term for these is plutonic. These are rocks that come from magma. They have cooled very, very slowly underground for sometimes millions of years. And what that allows them to do is grow crystals. Here we have a pretty nice piece of granite. And we have our weathered surface right here. Turning it over, it's been broken open, and we can actually see some crystal faces in this rock. What that tells us is this rock cooled rather slowly. Another example is this guy right here. You see some really big plagioclase crystals in this rock. So this rock started to cool very slowly, and then something happened where the rock was expelled onto the surface, and the rest of it cooled rather quickly, which is why we really don't see any mineral grains in what's called the ground mass of this rock. Something else that can help us look for crystals and minerals is a hand lens. This is what geologists use to check out the grains in a rock. I'm going to show you the proper way to use a hand lens. You want to hold your mineral sample up to the light, get it real close to your face, and adjust the distance between the hand lens and the rock until you can see those mineral grains clearly. And now what that enables me to do is get a better idea of what this rock is actually made out of. So those are our two types of igneous rocks. Intrusive igneous, cooled slowly underground. Extrusive igneous rocks came from volcanoes, erupted onto the surface, and they cooled quite quickly, meaning that they didn't get much chance for crystals to form in them whatsoever. So moving on, let's talk a little bit about our sedimentary rocks. Sedimentary rocks are rocks that come from sediment. These are composed of other rocks and materials that have been broken down through a process called weathering and erosion. So here we have a couple different samples of our sedimentary rocks. First one I'd like to show you is sandstone. So sandstone is the Nevada state rock. Sandstone can be the depositional environment that sandstone would have been formed in would be, say, maybe a dune, sand dune deposits, or even a beach shoreline environment. We also have another sedimentary rock called limestone. Limestone is a really common sedimentary rock in Nevada. It's full of fossils in many localities. These limestone samples actually have a couple of really nice fossils in them too. These guys are called Brachiopods, and they're found all over the place in present-day eastern and central Nevada. What these rocks tell us is that when they were deposited in a marine environment, which is why we see these fossils in these samples. Another sedimentary rock I'd like to show you, and something else I'd like to point out about sedimentary rocks, is that sedimentary rocks have layers. This particular rock is a great example of how sediments can be deposited and then solidified over time. So through a process called compaction and cementation, these grains that have all come together in a low-lying area or on the banks of a stream are then buried a little bit, but not buried enough for them to get too hot, but they're buried, and through that process of compaction and cementation, those sediments then smush together and form a much more solid rock like we see here. So the third and final rock type I'm going to discuss with you today are metamorphic rocks. Metamorphic rocks are rocks that have been changed from something else. These are rocks that have been maybe changed from an igneous rock or a sedimentary rock or even another metamorphic rock. Metamorphic rocks can form in environments that have high heat and high pressure. Sometimes maybe they'll have low heat and low pressure. And even we'll find environments that they form in with high heat and low pressure, or high pressure and low heat. It's a wide scale where these guys can form. So basically what happens is when one of our existing rock types is buried underneath the surface, and through plate tectonics and faulting and folding and additional deposition, these rocks can get buried deeper and deeper. And as they get buried, as they are buried deeper and deeper, they change. The minerals in these rocks change and turn into a harder rock, and sometimes we'll even get new minerals growing. Here's a great sample right here, and this is a gneiss, spelled G-N-E-I-S-S. It's a pretty nice rock. We see some banding and some larger grain crystals in it as well. And what's happened to this guy is it was buried, and over time things have started to grow and recrystallize in it. But keep in mind, if you have a rock that gets buried and it's buried too deep, it will melt, turning it back into magma. And so therefore that would just completely end our rock cycle, and we would start all over from the beginning, and that magma would either solidify in the magma chamber like we discussed with these intrusive igneous rocks, or it would be erupted out of the volcano onto the surface and turn into our igneous volcanic rocks. So Remember, if your rock completely melts, we're starting our rock cycle all over again. We have a couple different rock, metamorphic rock samples here that I'd like to share with you. We have something that's called a phyllite. So this phyllite originally came from a rock, a sedimentary rock, kind of like this guy, which would be more of a shale. So as this shale is buried underneath the surface of the earth, it gets exposed to heat and pressure. It turns into something called slate. That slate then is buried even deeper, maybe it gets a little bit hotter, more pressure, and it turns into this guy called phyllite. And the biggest difference we can see between these two rocks is this one has crystal, or this one does not have crystals, but this one does. And we can see these the shiny crystal faces on this guy. This is because it's been buried and its chemistry has, or its composition has been altered a little bit. If we keep going down through the various degrees of metamorphism, we'll end up getting to a schist, which is a rock that has a few more crystals in it. It's really common to find garnet minerals and schist. And then continuing on, we'll get to something like this gneiss that I showed earlier. Another one I'd like to point out is what our limestone turns into after it's been metamorphosed. So here's our nice friendly little limestone. He formed in a marine environment, had a lot of fun there, got some fossils in him, but then he got buried. And it got hot, under pressure. And what then happens to that limestone is it turns into a metamorphic rock called marble. Marble is a really hard rock, and that's why you'll often see sculptures, city buildings, countertops made out of marble. And so Galena and the Galena Creek Visitor Center and Galena Creek were all named for the mineral galena, which was found associated with gold ore in this area back during the Comstock days. However, no actual gold was mined in this area because of the low ore content and the amounts of galena that were found with the gold. So this region turned into a little settlement where logging occurred, and the trees that they logged ended up providing the timber for active mining up in Virginia City. So here I have a couple pieces of galena. Galena is lead sulfide. It is equal parts lead and sulfide, and its crystal structure is cubic, which allows the rock, or the mineral, to form these nice, really beautiful cubes. And when it breaks along those 90-degree fractures.